Welcome back. So, this is lecture 51 in this course on Bayesian modeling. The topic of this lecture is cross-validation with BRMS. In the previous lecture, we see how we can implement cross-validation in R. So, we took a simple example and we implemented the cross-validation method using a simple for loop in R. Okay. In this lecture, our goal is to do cross validation in practice. So, when you have experimental data and when you have some hypothesis of interest that you want to test, then in that case, how do we use cross validation for hypothesis testing, right? So, cross validation can be used for hypothesis testing, right? So, that's our goal. That's what we are going to do in this particular lecture. So, how to do cross validation for a real life experimental data and using BRMS, because you will need some better posterior estimation method, because for real life data you will have non-conjugate prior. So, you will have to use either HMC or MCMC. So, we will see that how we can do all this thing with BRMS, right. So, logic of cross validation will remain the same, the idea will remain the same, it's just that we are using BRMS for estimating the posterior distribution of parameters. Okay. So, let us see. So, you have this data on word recognition. So, we created in one of the previous lectures. So, the data is word recognition data.csv. I am reading from this CSV file using read.table function. So, this is how data looks like. So, it has subject ID, item ID, basically word ID, string type, word or non-word, frequency, high frequency, low frequency, all that, right. So, the variables of interest for us are these frequency, length, RTs, right, and type, whether it's a word or non-word, right. You can actually check the histogram of recognition times, because we would decide what likelihood function you're going to use based on the distribution of these RTs, right, and it looks like a log normally distributed recognition times, right. So, whenever we set up our model, we should choose a log normal likelihood, because that would be a more reasonable assumption. Now, the hypothesis that we are interested in testing is this, that high frequency words are recognized faster than low frequency words. Okay. So, this hypothesis is only about words. So, there is no non-words here. So, we are going to test this hypothesis only on data from words, right. So, if you want, you can split that here, right. So, data word subset that I think string type is equals to word. This will give me just word data. Okay. You can check how many rows are there. So, 10,000. Actually, it's a really big data set still, right. How many were there in actual data? Should be 20,000. Okay. So, I have split it into basically we are only going to use words data, not non-words data. Okay. So, first now we need to define our model. So, these are our model assumptions, that recognition time for the ith word comes from a log normal distribution with mean mu I and sigma. So, these are model parameters. Now, mu I is a linear function of alpha plus beta into frequency. That's all we need here. Okay, frequency of the ith word. Okay, so if it's a high frequency word or a low frequency word, that's it. And here, and what does hypothesis 1 predicts? So, H1 predicts that beta should be less than 0. So, basically, as frequency increases, the recognition time will decrease, right. So, it predicts that beta should be less than 0. Okay. So, of course, you can, based on whatever posterior distribution you get for beta, you can say that whether your data is consistent with the predictions of the hypothesis or not, but that's all you can say. You cannot make a claim about evidence. We discussed this point earlier. In order to make a claim about evidence, you need to do model comparison. Okay, and that's what we are going to do now. We are going to quantify how much evidence is there for this hypothesis 1, that is high frequency words are recognized faster than low frequency words, right. we're going to quantify how good is this model at predicting this recognition time data compared to, let's say, a baseline model which assumes that there is no effect of frequency on words. So basically the model that assumes beta is equals to 0. Okay? So that's what we are going to do. So for model comparison, you need to specify what are your competing models. So your first competing model is like this. So the likelihood will remain the same. Okay. So likelihood is RTI comes from log normal mu I sigma, and then mu I is equals to alpha plus beta into frequency I. So let us call it the frequency effect model. This is my model M1 and I'm calling it frequency effect model. Okay. Here you need to set up some prior on beta. We are assuming that beta will have some effect on recognition times. So let's say you set up normal 0, 0.5 prior on beta. Okay. So this is a model that assumes that there is some effect of frequency on recognition times. Okay. Now M2, you can call it a null hypothesis model or a baseline model or zero effect model. Another way to call it zero effect model. Okay. So what this model will assume, everything else will remain the same. It's just that the model will assume that beta equals to 0. Basically, effect of frequency on recognition times is 0. Okay, so there is no effect of frequency on recognition times. Okay. Now we will compare model 1 and model 2. If model 1 is better at predicting future data, then we can conclude that a model that assumes that there is an effect of frequency is better than a model that assumes there is no effect of frequency. So then we can conclude whether there is an evidence for an effect of frequency, or whether a model that assumes the effect of frequency is better than a model that does not assume an effect of frequency. Okay. So that's what we are going to check. So this we can do using model comparison. Okay. So how do we do cross validation here? Okay. So how do I begin? So I will start in the same way as we did for the previous part. So let's say I will choose 10 folds. Okay. 10 folds of training data and test data. Okay. And what we will do in each fold? For k in 1 to k. Actually 10 will require a lot of computation, so let's say just 4 folds. Okay, but you can go up to 10. It's okay. Actually typically people use 10 folds, right? You should use 10 folds in real in when you are doing it right, but it's just that to save computational time we are using 4 folds here. So for k in 1 to k. Okay. So one thing we need to do now is to split our data into training set and the test set, right? Actually they are basically you can also do it even before going inside this. So basically let's say let me call it y test and it's a list, and let me call it y train, it's another list, it's an empty list for now. Okay, and this is another empty list for now. Okay. Okay, so y test will be residual. Okay, so what's the method we use? So we create residual equals to entire data, right? Now y test will be, test set will be sample from residual. So you can use sample n function. So this is used for sampling observations. Okay, how many observations you want to sample? So we are using 4 folds. So basically it should be how many total observations you have? 10,000. So in each fold there should be how many? 2,500. So let's say sample 2,500 observations here. Okay, and what else? Yeah, this is fine. And now the remaining residual will become difference of data frames. So let's see if it works. I'm not so sure. Why couldn't find function sample line? Okay, it's in library dplyr. So let me load library dplyr. So now this should work. Yes, so it contains 2,500 rows, and if I set this set difference, what would it give me? Okay, looks like 7,500. So it is working. Okay, so everything is fine. Now y train would be set if dat dot word y test. So the remaining one is y train. Okay. So this is for kth fold. Okay, fine. So up to this point, we have test data and training data for each fold. Okay. Now comes the real part, which is estimating the posterior distribution. So estimate posterior, or rather than saying this, let us say fit M1 model 1 to training data. Okay, so how do I fit model 1 to training data? What is model 1? Actually, I can copy paste from here for now. Let me take this Let me define this library BRMS here. Fine. So M1 is actually BRMS recognition time predicted by 1 plus frequency M, right? Data is Y train, because that's the data we are going to use to train the model. Family log normal, A, B, actually beta we assumed was 0.5. I mean, that's the prior we took. Sigma, okay, and normal. So everything else is fine. So this will fit model 1. Okay, but we need samples, posterior samples from model 1. Okay, so how do I get posterior samples? Like this. Okay. We do not have type predictor, so we can remove this. Alpha M1, beta M1. Okay, so now we have posterior samples for alpha and beta. Okay, this is fine, but our job is not done yet, right? We need to now calculate ELPD for model M1. So how do we do that? Yeah. So what we need to do, we need to iterate through actually each data point in our test set, right? So for I in 1 to length y test, which was for example 20. Oh, y test is 10 here. I don't think it was 10. Okay, not length, and row. 2500, right? So number of rows would be 2500. So for each row, okay, in your test data. So what we are going to do, we are going to calculate LPDI. How do we do that? Given these posterior samples, we will first calculate mean of likelihoods. And what is likelihood? DL norm. So DL norm data is y test I, y test RTI. This is data point, ith data point. For this ith data point, we will calculate this thing RTI using mu I. What is mu I? Alpha plus beta into frequency I. So basically alpha posterior, so posterior samples from alpha 1, posterior samples from beta into frequency. Y test frequency dot m, right? I. Okay. So this has become mu, and then also sigma. So you have sigma posterior as well. So how do I get sigma posterior? I don't know what kind of output it gives me. Do we have M1 here? Oh, sigma. Yes, we have sigma. So it's fine then. So I can write, I can retrieve sigma as well. Okay. So this will calculate log predictive density for ith data point. Take its log. But now we should basically calculate it for all data points, all 2500. So I will write overall LPD for kth fold. Okay. This will be faster if I do this. So directly done this, right? So I will just directly store all LPDs, LPD1, LPD2 like this in this frame, right? So this will give me LPD for the kth fold. Okay. Now I can calculate ELPD for the kth fold. How do I do that? I have LPDs for each ith data point. So it would become mean of ELPD K. Mean of LPDs, right? So I have ELPD K, right? But this is, by the way, for model M1. Okay, so that you should remember. So this is ELPD for kth fold for model M1. Now we will do the same process for model M2. Okay, same process for model M2. What is model M2? So model M2, there is no effect of frequency. Basically, remove this beta parameter. So remove this class B as well. Everything else remains the same. This is M2, 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 this is M2. Beta is 0. Everything else remains the same. Here in the formula, you remove this part. Okay. This is M2, this is M2. So this will give me M2. Now I have ELPDs for M1 and ELPDK for M2. Okay, so I can actually store them like this. Okay, so ELPDK M1 for the kth fold would look like this. ELPD Km2 for the kth fold would look like this. Okay. In output, you will get ELPD values for model M1, model M2 for each fold. So, basically you get 4 ELPD values for model M1, 4 ELPD values for model M2. You can take their difference then like this: ELPD K model M1 minus ELPD K model M2. If let us say these values are positive, then model 1 is doing better than model 2. Basically, then there is evidence for the effect of frequency. Okay. You want to run this. So, this will take time, but you can try this yourself. So, what I did was that I first created this test set by taking out these 2500 observations. Then I took the remaining one as training set. Then I trained my model on this training set, right? And so I got these posterior samples for alpha, beta, and sigma. Now I use these posterior samples from alpha, beta, and sigma to test, to compute LPD, log predictive density of the model, using test data, Y test, right? So I do this for all test data points, right? And then I do the same process for model M2. So eventually what I will get is ELPD values for each fold for each model, and I can take their difference to see whether model 1 is better than model 2. Okay. I can run this, but I'm not going to finish this computation in time. So you can try this at home. So it will keep showing this message for a while. Okay, so you can try it yourself. I can upload this file on NPTEL. All right, I'll stop here. So this is it on cross validation. So we have covered that how do we do model comparison using this idea of expected log predictive density, and especially when we do not have access to future data. So you can split the existing data into multiple into training sets and test sets, and then we can train the model on one portion and test its accuracy on the another portion. And we saw how do we implement it in R as a simple sampler as well as using BRMS, right? Now you can practice on this. So basically this is one of the important method in model comparison, but this is not the only method. In fact, you will see that for hypothesis testing, for the kind of hypothesis testing we do in cognitive sciences, actually Bayes factor would come in very handy. So that's another method of model comparison, right? So we'll learn about Bayes factors in the next few lectures, right? But you can practice cross validation, because this is also a very important tool. Especially it will become important if you do complex cognitive modeling, right? When you work with complex cognitive models like drift diffusion models or other models, right? But if in the next lecture we will start Bayes factors, which is another very important tool for quantifying evidence in the Bayesian framework. Okay, so I will see you in the next lecture. Thank you.